So next we'll look at some commonly used properties of the normal distribution relating to converting normal variables. And again, this should be familiar. That if we have a normal random variable that has a mean of mu and a variance of sigma squared, we can convert it to a standard normal. And the standard trick is we subtract the mean and divide by the standard deviation. And we'll understand this in a minute. So what we're saying is that if x is normal, mean mu and variance sigma squared, the random variable z, which we're defining as x minus mu over sigma, that random variable has a mean of 0, variance of 1, and it's normally distributed. So there's really three points made in this statement. One point has to do with the mean and the variance, which is probably transparent, but we'll see that in a second. And the second one is the actual distribution of z. Conversely, if we have a z, which is normal, standard normal, by multiplying it by a number and adding a number, we convert it to a different normal. So again, there's three statements in the second bullet. The first is that if we add mu after we multiply the standard normal by sigma, there's three things that we've done. First is we now have a random variable with a mean of mu, a variance of sigma squared, and it's still normal. So again, three different points. So as in the example here, we see if x is normally distributed, mean of 3, variance of 25, and z is normal, then we can go from an x to a z very easily, namely that x minus 3 over 5 is standard normal, and 5z plus 3 is in fact the original normal x. So how do we justify this? Well, the moment conclusions are fairly straightforward. They're just using properties of expectations which you should be familiar with. So for example, if I looked at the expectation of a random variable x minus mu over sigma, well, property of expectation is it's multiplicative. I can factor out the sigma, and the expectation of a sum is the sum of the expectations. So I get 1 over sigma times the expectation of x minus mu, which of course is 0. Similarly, the variance, using properties of variance, since the expectation of this random variable is 0, the variance is simply the expectation of that random variable squared. So this is just the expectation of that random variable squared. Well, again, using properties of expectations, I can factor out the 1 over sigma squared, and I have left the expectation of x minus mu squared. Well, that's by definition the variance. So I have the variance divided by the variance. No surprise, I get a 1. And using exactly the same, and I'll leave it to you as an exercise, using exactly the same properties of the expectation, you can work the other way around, and that is that you can prove or derive that if I have a standard normal z, that if I look at mu plus sigma z, that this has a mean of mu, and if I look at the variance of mu plus sigma z, I indeed get sigma squared. So the moment consequence would be, in fact, fairly easy to derive just using properties of expectations. And in fact, what we just did had nothing to do with the normal distribution. If x and z have any distribution with the means and the variances quoted, then by doing the transformations that we did, we would get random variables with the stated means and variances. This has nothing to do with normal. What's interesting and important about this prior slide is the normality of the random variable x minus mu over sigma. And also the normality of mu plus sigma z. It's the preservation of the distribution that is the less obvious, perhaps, consequence. not the moment values. So let's look at that. And the reason that the probability distribution is preserved, that you go from normal to normal when you do these linear transformations, is really a byproduct of the moment generating function. And I'll just remind you of two things. First of all, the moment generating function of any random variable is by definition the expectation of e to the xt. Hopefully you recall that. And it turns out that if x is normal, with a mean of mu and a variance of sigma squared, we can determine its moment generating function. It's an integral. It involves some completing the square and some substitutions, but it's relatively straightforward integration. And you find that the moment generating function of a normal is e to the mu t plus a half sigma squared t squared. The other important, so of course this works with any mu and sigma. We can plug in a 0 for mu and a 1 for sigma squared, and we get the moment generating function of the standard normal. The important observation about moment generating functions is that they're unique. The only probability density function that has this moment generating function is the normal distribution mean mu variance sigma squared. It identifies the probability function that you're dealing with. So the way that we can prove, I'll do one, and again leave the other as an exercise. The way we can in fact prove that x minus mu over sigma is indeed normal. Not that it has a mean of 0 and a variance of 1, that's the easy part, but in fact it's normal, is we're going to prove that the moment generating function of that random variable, and let's just call it y, just to save a little bit of notation. We're going to show that the moment generating function of that random variable y is in fact e to the 1/2 t squared. Well, if I look at the moment generating function above it, there's only one random variable that has that moment generating function, and that is the normal distribution with a mu of 0 and a sigma of 1. And it's just that simple. It's the important characterizing property of moment generating functions. When they exist, they characterize the probability density function. So how would we do that? Well, let's just do the math. We have to calculate the moment generating function of y. And this is by definition the expectation of e, and then we have to take the random variable times t. So now let's put in what that random variable is. It's e to the x minus mu over sigma. Okay? And now what is this? Well, this is I can split up the exponent of the exponential and factor out a constant, the constant being e to the, and there's a t in there, sorry. I can factor out the constant relative to the expectation of e to the minus mu t over sigma. That's a constant in the expectation because the expectation is relative to x. So I can just factor that out as a multiplicative constant, and I'm left with the expectation of e to the x over sigma t. Now remember, x is normal, and it has a mean of mu and a variance of sigma squared. And if I look at this, I notice that this is the moment generating function of a normal x calculated at the value t over sigma. So I can use this result I have above. I know exactly what the moment generating function is of that normal variable, and I want to evaluate it not at t, but I want to evaluate it at t over sigma. And when I do all the substitution, what I finally get is I have e to the minus mu t over sigma. That's the multiplicative factor we factored out. And then the moment generating function of this normal x at the point t over sigma we see above, and that's equal to e to the mu, and we want to use t over sigma for t, plus a half sigma squared, and again we want to use t over sigma for t because that's where we're evaluating it, and you just multiply that out, and lo and behold, you get e to the 1/2. There's a square there that I missed, sorry. E to the 1/2 t squared. Just a little bit of algebra, and you just need to carefully follow it through. But what we saw is that if x is normal with the appropriate mean and variance, then this transformed x minus mu over sigma, in fact, has the moment generating function of the standard normal. Therefore, it has to be the standard normal. It can't be anything else. And you can try the alternate calculation, namely if you start with a z and transform it to mu plus sigma z, you will find precisely the same thing, that random variable has the moment generating function of the normal with a mean of mu and a variance of sigma squared.